like the way you already have your simultaneous equation back from the senior high you were doing, right? You can be given like some three linear equations, like equation one, equation two, equation three, and then you can be asked to find the unknown variables in that. In here, you're going to be given some n set of linear equations, and by now you should know what a linear equation is. A linear equation is any equation that the highest power of the unknown variable is 1. Okay, so that's basically what a linear equation is. Please, are you sharing your screen? We cannot see. Yes, I'm sharing. Can you all see my shared screen?
Yes, we can see it.
Yeah.
Okay,
Yes,
please, those
We
sir.
can see.
kindly exit the call and join again if you cannot see my share screen, right? All right, that's fine. So as I mentioned, linear equation is any equation that the highest power of the unknown variable, in this case, your unknown variables are x1, x2, x3, all the way to xn, are having a highest power of 1. We know what a power is, we know what an exponent, we know what an index is. They are all used interchangeably, right? So this is a linear equation. This is also an example of a linear equation. Also an example of a linear equation. Why? Because the highest power of the x, right, is what? It's 1. This is x1 raised to the power 1, x2 raised to the power 1, xn raised to the power 1, all the way to the rest down there as well. So linear equations are common and important for survey problems. Matrices can be used to express these linear equations and aid in the computation of unknown variables. So anytime you have this set of linear equations, we can represent them as a form of a matrix with the equation AX equals to B, where A is what we refer to as a matrix of coefficients. And these coefficients is A11, A12, A1n. And when we come here, we have A21, A22, A2n. And when we come here to the coefficients is AN1, AN2, all the way to ANN. And this ANN will let you know that we are dealing with a square matrix. So with a square matrix, we can have the coefficient matrix as A, which basically will be this. Okay, so that's what you can see here. So A11, A12, A1n, right, which represent the first equation you are seeing here, right? The coefficients. And then the second one, which is A21, A22, all the way to A2n, is what you are seeing here. And lastly, we can now see AN1, sorry, this one was supposed to be AN2, not ANN, right? So this one is supposed to be AN2. Sorry about that, I'll correct it now, share. And then ANN all the way going down, right? Then we come here, the same thing here. So we can have how many equations? If you check, equation 1, equation 2, equation 3, all the way to equation n. So there are n equations in n unknowns. N unknowns because the variables x1, x2, x3, all the way to xn are having a total of n unknowns. And then the aij's are numerical coefficients, which are the coefficients of the x1, x2, xn, right? When they come here to the same thing, okay? So as I mentioned, sorry, Junior, stop writing on the screen. Okay. All right, so when you come here, you can see we have AN1, AN2, ANN. So if you come here, please, this is supposed to be AN1, AN2. This is AN2, not AN1 here again, okay? So that's the matrix of coefficient. And then we can now have this one as the vector of xi unknowns. Then we can have the b, which is the bi's, right? The vector of bi's. So the equation that you see here can be expressed as ax to be equal to b, right? Where the a is a matrix of coefficients, aij's. The x, which is what you are finding, the unknown x1, x2 to xn. And then the b, which is b1, b2, which you can represent as what, n by 1. And then there's also a matrix with the dimension n by 1. And lastly, this is a matrix by the dimension n by n. So in that case, we can now find x. Now in finding x, we need to still use the rules we know as far as what we learned last week is concerned. So I can multiply here by what we refer to as the inverse of A. Okay. Now, whatever I'm doing to the left hand side, I have to do the same to the right hand side. So here too, I have to also have some A inverse here as well. So that to be A inverse times the B. Okay, I've not changed anything in the equation. I've just added multiplying the A inverse to the left hand side and the right hand side. Now, when we do that, you realize that the whole of this will tend to be I, the identity matrix I. Okay, last week you saw what an identity matrix is. An identity matrix is any square symmetric matrix whereby the leading diagonal elements are all 1, and then the off diagonal elements are all 0. So that is it about the I here. In that case, we can now say that I times X. Last week we saw a property that if you have the identity matrix times any matrix or vector, it's the same as that vector or matrix. So I'm going to have X to be equal to the inverse of A multiplied by the matrix B. And that basically becomes a formula. So means that anytime you have this set of equations, if you're able to get the coefficients, like we have it here, and then you're able to extract the unknown variables x1, x2 to xn, then you also know the known variables b1, b2, bn, which is the right-hand side here. You can now easily be able to now use the formula x to be equal to the inverse of A multiplied by the matrix B. That's it. So what do we need to do? All we need to do is that we need to be able to go through the problem or the headache of getting the coefficient of this matrix. Once we get a coefficient of this matrix, we now need to multiply it by the known vector B. That's it. Okay, so that's what we have to do. So what I've proved here is this, right? This is what I just showed you. Now, once we have that, let's look at an example. So we have an example. I picked a basic example from what you guys were doing back in the senior high, right? You have 3x1 minus x2 plus x3 to be equal to 2. We have 2x1 plus x2 equal to 1. x1 plus 2x2 minus x3 equals to 3. Now, with that said, all we need to do is that we want to be able to get this x to be equal to the inverse of A times B, what we saw earlier on, right, from the previous slide. So what we need to do is that for us to be able to get this, we know that this came from AX to be equal to B. So all we need to do is get the A, get a B. Of course, we know that the X will be how many unknowns? So X will be X1, X2, X3, which you can see here. Can you see that? Now, for us to be able to get the A, we just have to put the coefficients. So the first coefficient is 3. So that's what is here. The second coefficient is what? -1. That is here. The next coefficient is 1. That is what is here. Then when we come to the second one, we can have another coefficient, which basically is going to be what? This 2. That is what is here. And then the next coefficient of x2 is 1. Okay? So you can see that there's a 1 multiplying the x2. Although you cannot see it, any number multiplying a variable is the same as what? The variable. Right? If you have a number like 1, sorry, multiplying a variable is the same as that variable. So at this situation, you don't need to see 1 written here, but at this situation, there's a 1 here. So that's why there's a 1 here. And the next one is the coefficient of x3. Of course, there's no x3. So because there's no x3, what do we need to see? We need to be able to see that this guy will have a coefficient of what? 0. Because 0 times x3 will give you 0. So that's why you cannot see any x3 here. Because that coefficient will be 0. Then lastly, we can now go ahead to be able to see the next one, which basically is a coefficient of x1, which is also 1 here. Can you see that? So there's a 1 here. And then that's it here. Then look at the coefficient of x2, which is 2. And that's what is here. Then lastly, look at the coefficient of x3, which is what? -1, right? Why? Because the negative is affecting it. This one is +2. This is also +1, but you don't bring the plus there. So that's it. So that's it about the coefficient of all the unknown variables in the three set of equations. Now, with that said, we can easily now be able to also get the known variables for the B, right? So with that said, I can now pick these two as a first B1. Now bring it here. I pick this one as a second B2. I bring it here. And this as a B3. Now also bring it here. So now the formula says that this is the same as your AX to be equal to your B. That we already know. So we need to be able to find our X. And in finding our X, it's going to be X to be equal to the A inverse times the B. That's it. And that's what you are seeing here. So our main headache is to find the A inverse. And last week you saw how A inverse is computed. So please, you have to revise that. If you want to be able to use the calculator to do that, that's up to you. But remember, the calculator can only be used when you have maximum of 3 by 3. If it is a 4 by 4, that is also another headache. So you need to be able to read on that as well. Okay. So once we're able to get a coefficient of A, we can now have this as a coefficient. Then now we pick the B, which is the 2, 1, 3, which is here. Then we can now do our multiplication. This is 3 by 3. This is 3 by 1. Okay. So from what we saw last week, 3 by 3, 3 by 1, the inner agrees. So that's going to lead us with what? A 3 by 1 again. And that's our final answer. 2 negative 3x. And that is the same as x1 to be 2, x2 to be -3, x3 to be 7. That's what you are seeing here. Sorry, you can see there's a mistake here. This guy shouldn't have any negative here. Okay, so please correct that. Let me see whether I can correct that one. Okay, let me see whether that part can be corrected. Just a second. Any questions so far on that? Yes, Idrisu.
Sir, please, my question is that AX is equal to B. Can you please make A this what do you call it? X.
Can you please what?
Get
Am I?
divided by A. So the A will cancel the other A. X is equal to B over A.
No, you cannot do that, please. We cannot do that division in matrices. Are we okay?
Okay.
Do you understand? Okay. All right. Any other further question? Frank,
So it looks like the -7 is right too.
it's right, eh? Oh, okay. Sorry.
Yes.
That means that what is in the bracket rather is wrong, right? So thank you. So let me correct that one rather. Okay, thank you. So this is wrong. So this one should be here. Okay. Please, any other further question? All right. With that said, I think that we're good. So this is supposed to be -7, please. Okay. All right. So some applications of matrices is something that we also have to quickly look at. So when you talk of this means more for me, okay. So linear algebra is one of the first application we need to know when you are dealing with matrices. Matrices are normally fundamental in linear algebra because, for example, this linear system of equation we just saw, this is also a typical example of what application of linear matrices in linear algebra. Okay. Again, we can also look at it in terms of computer graphics. Matrices are used in computer graphics for tasks such as representing transformations, right? Right, in terms of you trying to rotate or scale a particular image. Oh, I stop there. And then you can also be able to see how you can do some form of what translations as well. If you're also modeling some 3D objects in some form of animations, right? Maya and other stuff, you can actually use that to be able to do this. Performing perspective projection matrices can also be used to do that as well. Now, when it comes to data analysis and statistics, we can also apply matrices when we want to be able to represent some form of data set or observations or variables in a form of matrices, right? So that's another thing. I don't know. You can also use it in something we call principal component analysis, PCA. So in principal component analysis, when you get to final year and you're doing data mining, you'll be exposed to that. But basically what PCA does is that if you have a data set that has an overwhelming number of features and you want to be able to select or extract relevant features, you can use a PCA to do that. Then there's another concept we call machine learning and data mining. I mentioned data mining, you can do that. So in machine learning, you want to be able to make matrices do tasks such as feature extraction, dimensionality reduction, model training, etc. Okay. And you can also use the matrices to represent data. So if you have an image, you can represent that image as a form of a matrix with zeros and ones there. Again, in signal processing, right? Matrices are also used to be able to do tasks like filtering, convolution, spectral analysis, etc. And then for optimization, there are also things that you can also use matrices for. In fact, there are other ones there a lot, like physical engineering, network analysis. Talk about optimization. Use it to be able to do such linear programming, right? So the linear programming we are dealing with will have to do with something like finding an optimal solution when you want to be able to have a set of a particular main objective function subject to some constraints that you want to be able to deal with, right? So in this case, we use the matrices to represent optimization problems, basically like mathematical or statistical modeling. Matrix operations also are used in these optimization algorithms, like the multi-objective optimization functions and other stuff, right? The linear programming, the quadratic programming, etc. Right? So that's basically how matrices are applied. In summary, we can be able to say that a matrix basically is a square or rectangular array of numbers arranged in rows and columns, and we can actually be able to name a matrix based on the number of rows followed by the number of columns, right? And we saw that a vector is a single row or a column matrix. And then we also saw some forms of matrices: the identity matrix, the null matrix, the diagonal matrix, the upper triangular, the lower triangular matrix, etc. They also saw the inverse of matrices, finding the minors, finding the cofactors, finding the adjoint. And then when you have the determinant, you just reciprocate it and multiply by the adjoint. That'll give you the inverse of a matrix. Of course, we also saw lastly that matrices can be used to express linear equations in the algebra aspect, and we can also do the vice versa. Don't forget that when you have the matrices in terms of the AX equals to B, you can actually transform it back to get a linear set of equations as well. Okay. That's a recommended textbook. Any questions so far? Great. So if there's no question, we can quickly move on to what we have for today. That has to do with recursion and relation. Okay. So I'll upload this slide. I don't know whether I uploaded the last time. If I didn't, I'll do that. So we come back to somewhere your hand is up.
Hello, sir.
Yes, sir. Please, the inverse. Can you help me more to understand it more stronger?
Please get the tutorial class with the TS. They will explain it to you guys. Okay. Did you meet the tutorial session on Wednesday?
Oh,
Sir.
okay.
Yeah. If I don't take care, I cannot
Sir.
finish it. So that's why I've made an arrangement for the TA to be meeting you guys. Okay.
Sir, about the tutorial, we don't get the link, so.
Did you meet the last time, please?
No, please.
Yes, we met the last time we met.
Okay.
Yes, we met the last time.
The last time.
Okay.
Sir,
Please, your WhatsApp
please.
page, you should be active on that. If not, then maybe I have to be creating an announcement on Sakai, so that when the link comes in, you have to pay attention to that. Okay.
Okay, sir.
All right. Thank you.
Hello, sir.
Yes.
Please, about the determinant.
Okay.
So for finding the determinant, can you first apply the plus, minus, plus before you find it? If you do that, will it help? Will you still get the same answer?
I will advise you don't do that. Just find for the individual 2 by 2. If it's a 3 by 3, do the individual. When you are done, you just include the plus, minus, and find the final results. Okay.
But that one, is it that you are multiplying with the you are multiplying or you are replacing the plus minus plus?
So I'll give you a typical example here. So if let's say I have the debt of A to be equal to, maybe the first one I did, I had sum 2, then this one is, let's say, -4. Then I don't bring anything here, right? And I have another one to, let's say, -3. Then 1. Then lastly, I can have 4, 2. If I'm introducing my plus minus, right, let me use a different color. So I can bring my plus here, I can bring my minus here, I can bring my plus here. So what do we have? We know that this one is expected to be plus 2 times -4, that's -8. And this guy is -3 times 1, that's -3. Random minus, that will be +3. And lastly, I can have +4 times 2, that's what, +8. So with that said, I know that my final answer for the determinant will be what, +3. Please, you understand?
So
No,
assuming
sir.
that the 4 was negative, I mean that it will be negative over there, right?
Yes, it will be negative over there. Why? Because the plus coming here is like a +1 multiplying that -4.
Okay.
Okay. All right. So far good. So good,
Okay,
right?
thank you.
You're welcome. Right.
Okay.
So we're looking at recursion and relation. So for recursion and relation, these are the topics we need to cover. First one has to do with the recursive functions. The next one has to do with the binary, and then all the way hitting the equivalence and application. So at the end of the session, you want to be able to understand the following, right? You should be able to define functions recursively based on the basis step and the recursive step, which you'll be looking at shortly. And then you should also be able to understand the properties of relations. You should also be able to know equivalence of relations. When we talk of equivalence of relations, what does it mean? But based on the properties, we should be able to understand the equivalence. And lastly, we should also be able to know some applications of recursion and relation, because we cannot teach it in the maths point of view without relating it to how it plays a key role as far as computing is concerned. Okay, so that's what we have on the table for today. So when we talk of a recursion, Recursion normally is a process or an approach whereby we can define an object, or we can call an object a number of times, or we can invoke an object by itself a number of times. So some of the objects we can think of will have to do with the methods, the functions, the procedure, the subroutines, all the way to something like a sequence or a set. So these are various objects that can be executed by itself a number of times. So I can have a particular for loop that in any time t, I can always be calling a particular method to be able to execute that. So if I'm trying to find the circumference of a circle within the for loop, I should always be changing the parameter, in this case, the radius, a number of times and getting series of what? Maybe circumference. So circumference formula we know is 2 pi r or pi d, right? So that's something we need to be able to look at. So only consider the sequence of a powers of 2. So powers of 2, basically, if you are looking at it in terms of non-negative powers of 2, then we are looking at 2 to the power 0, 2 to the power 1, 2 to the power 2, all the way to 2 to the power n. Okay, so the terms of the sequence can be specified using a formula defined as a of n to be equal to 2 raised to the power n, where, as I mentioned, n will start from non-negative integers like 0, 1, 2, 3, all the way to some positive infinity. So when we are defining a function recursively, then our main key thing is to be able to see how best we can now be able to like identify the function based on two things, right? We got a basis step and what we refer to as the recursive step. So with the recursive basis step, it's normally defined at 0, right? The initial step. So if you have, let's say, 2 to the power 0, 2 to the power 0 is the lowest power of 2 we can actually be able to think of. So with 2 to the power 0 giving us a 1, which is the same as the first value in the sequence A0 to be equal to 1. And then from there, we can now be able to see how we can get subsequent values from that A0 of 1. So if I'm at A1, it means that the next one I'm going to do, if my n is 1, I can move on to A of 1 plus 1. If my n is 2, I can move on to look at A of 1 plus 2. If my n is 3, I can move on to look at A of 1 plus 3. So it means that the down one should be given as something like what? A of n plus 1, where that n here should be able to keep track of the incremented value to move me from a lower level to an upper level. And as I'm moving to an upper level, I need to be able to make use of an initial value, which we are referring to it as what? You are recursively, or you are invoking the previous value to make room for the subsequent values, okay? So that's it here. So that's why we have the A of subscript n plus 1 to be equal to 2 of an, where here, if my n is 0, I'm going to have here to be 0. Can you see that? Pay attention here. 0 plus 1. That should be able to give me what? A of 1. And then this one to be equal to 2 of what? A0. Why? Because I'm using n to be what? 0. Now watch this. Because A is 0, I already know from here that A0 is 1. So that's now going to give me 2A0, which is 2, 1. Which is the same as 2. Now this 2, 1, which is the same as 2, if you check very well, when I had my 2 to the power n, and my first value was 2 to the power 0, that gave me 1. The next thing I have to now look at is when n is 1, right? I can now go and have the other value, which is now going to be also going to have 2 to the power 0. which is what I have initially as 1. And the next one is 2 to the power 1, which is 2. The next one is 2 to the power 2, which is 4. So this one is what you are seeing here. Oh, sorry. As a basis, sorry. Let me use a different color. This one is what you are seeing here. Another color here, maybe let me use light blue. This one is what you are seeing here. So if I want to get 2 to the power 2, all I'm going to do is that I'm going to place this n, increment it from 0 to 1, and that'll give me a of 1 plus 1, which is the same as what? A of 2. To be the same as 2 to the 2a of n. In that case, that would be 2a of what? 1, because n is 1. Now with a of 1, I know from here, a of 1 is what? 2. So that's going to give me 2 times 2, which is now going to give me 4. Any
Sir,
question? Yeah.
sir, please, so how about the A, 2A? Will you, is it that you are going to put the two that you are talking about, we are talking about, the 2 exponent 1? Are we going to put it at where the A is and multiply it by 2 to get a 4?
So we do it sequentially, right? At the onset, you are given a base or an initial value, which you call a of 0 to be 1. Okay? And this a of 0 to 1 is the same as 2 to the power 0. And now the question is now asking you, you have a of n plus 1 to be equal to 2a of n. So what the question is saying is that complete the sequence up to, let's say, n equals to 5. So if n is supposed to be equal to 5, you need to start with n of 0. In other words, n equals to 0. If n is equal to 0, that's what I did here. A of 0 plus 1. And that should give you 2a of 0. And I'm calling a of 0 because I already have a of 0 here. So I'll just do the substitution. That is just going to be 2a of 0. Then it's 2 times 1 because a of 0 is 1. So this one is going to give me 2, 1.
Okay.
Which is the same as my 2. And this 2 is the same as 2 is the power 1. Then the next thing is that if I want to be able to get this guy, which is 2 to the power 2, then all that I need to do is first make another substitution. This time around, instead of saying that my n equals to 1, n equals to 0, I'll not say n equals 0 again, but I'll rather say n equals to 1. Because I did n equals to 0 in the previous iteration. So this one will be n equals to 1. And if n is equal to 1, this is going to be 1 plus 1, which is now going to give me what? A2. To be equal to, when I come here, 2a, remember our n is what? It's 1, 2a1. So that 2a1, I know my a1 for the previous iteration is 2. So that's now going to give me 2 times 2, which will give me 4.
Okay.
And that 4, check, is the same as 2 to the power what? 2. So far, so good.
Yes, sir.
Okay. Is any other further
Hello.
question?
Hello, sir.
Yeah.
Please, can you take the A2 is equal to 2A1 again? Not getting.
A2 equals to 2a1. So here, I did a substitution of n equals to 1 because I've done substitution of n equals to 0 in the previous iteration. So I did n equals to 1. If n is equal to 1, this will be n, which is 1 plus 1. That will be a of 2 equal to 2a1. N is 1. That's why I have 2a1. And what do I know for a1? A1 for the previous iteration is what? Is 2. So that's going to give me 2 times 2, which is 4. And that 4 in terms of powers of 2 be the same as 2 to the power 2. Please, are you okay now?
So now I'm not seeing right around.
Okay. But I think we can move on, right? So the next thing on the table, has to do with this one I just mentioned. How we can define functions recursively, and then based on the basis. So the basis step is what we having basis step to specify the function at 0, and then the next one is the recursive step, whereby you can be able to generate something like this, right? The 2an from that. So you look at it, and then you check the trend of what is giving you. Then you can now define your recursive step. So give a rule for finding its value at an integer from its values at the smaller integers, right? So always it is going to recursively calling the previous value starting from the initial value. Then you get the next one. The next one will now get it from the current one. The next one will also get it from the next previous one again until we are good. Okay, so it has to be calling it recursively. So we have this example, give a recursive definition of a of raised to the power n, where a is a non-zero real number and n is a non-negative integer. So a of 0 equals to 1, which is the basis. And then we can now have the next one, which is a raised to the power n plus 1 to be equal to a dot a n for n equals to 0, 1, 2, 3. And that's going to be defined recursively. Okay. Now let's look at this example. Let's see whether we cannot try it, right? So when we consider a function f defined recursively as f of 0 to be equal to 3, and then f of n plus 1 to be equal to 2f of n plus 3. Our main bone of contention here is to find f of 1, f of 2, f of 3, and then f of 4. Can we all try?
Yes, sir. So we are trying.
All right, sure, good.
Sir,
Yes, please, I can hear you.
okay, so I'm done.
So I'm
And-
also done.
Okay, please hold on small. Let's give others a few seconds to try. Okay. All right, thank you. Okay, so I think we can continue. Please, what did you get for F1?
I got F1 to be 9.
Okay, so how did you get F1?
In calculating F1, that's what I did. F1 is equal to 2F since we were given f of 0 to be equal to 3,
Nice.
it is something we can relate to. So it's going to be f1 is equal to that's 2f of 0 plus 3, which will give you 2 times 3 plus 3, which is equal to 9.
Okay, so what was the first initial assumption you made for the n value? To be
Pardon?
able to get F1? What initial value did you assume to get F1?
What initial value did I assume?
For n to get
For
F1?
0.
Yes. So guys, did you follow that? Okay, n has to be equal to 0, so you can get F1. If your n is equal to 0, if you check what, you realize that the whole of this part will be 0, right? If I make this n to be 0, then what am I having? It means that I'm going to be able to have 0 plus 1. That is n equals to 0. That's making a substitution n equals to 0. Please, are we okay? So if I do that, then I can have my f of 0 plus 1 to be equal to 2f of 0 plus 3. And that is now going to give me what? My f1 because it's what? 0 plus 1, which is f1, to be equal to 2 f of 0. Are we good? Plus 3. Good. With that said, we already know f of 0 to be 3. That's what you were saying. Can you see that? So let me just see whether I can use a different color. So this part is here. So now I can have my 2 times f of 0, which is 3. That'll give me what? 2 times 3, which is 6. Okay? And that's going to give me, 2. Please, if I bring a dot here, it means times. Let me just write times here so that someone will not come and ask me. 2 times 3 plus my 3. This situation, there should be brackets here, right? So that you know we are multiplying the 2 and the 3 first. And this now should be able to land me up with what? A 9.
Yeah, 9.
Now, with that said, it is obvious that if I'm able to get my f1 to be 9, then to be able to get my f2, all I need to do is that I need to increment the n, which was initially 0, to n equals to 1. So in that case, here will be n equals to 1, right? And then in that case, this will be 1. Now, if you check that, right, so n is equal to 1 is the next assumption to make. And when you do that assumption, you can easily be able to get your next value, which we and I know we are getting f of 2, right? So this will be f of 1 plus 1. That'll give me f of 2 here. So that will be f of 2 to be equal to 2f of 1 plus 3. And what is f of 1? F of 1 is the 9 here. So I just have to make a substitution. That'll be 2 times 9 plus 3. That's going to give me what? 2 9 is 18.
21.
21. That's it. If I also want to get f of 3, then I have to also go ahead and make what? Substitution n equals to 2. Okay? If I do n equals to 2, this one will be f of 2 plus 1. That'll be f of 3. And in this case, that will be 2f of 2 plus 3. And f of 2 is a 21 you mentioned for the previous iteration. So I recursively call that guy and I do it. Then lastly, if I also want to be able to get a next one, which is now going to be n raise the to get f of 4, then I have to now make a substitution n equals to 3. So that would be f of 3 plus 1, that would be f of 4, to be equal to 2f of 3 plus 3. And f of 3 from the previous iteration, we had it. So we can now be able to go ahead and then now get a final value. So if you do it, this is what you expected to get. And I hope you all had it. Any question?
Yeah, please, can you give another question? Let's see that. Yeah.
Oh, so please, that's why the tutorial is there. I've just seen that Kelvin, please, how are you? I've just seen Kevin has posted something on the page. Kevin is my TA, so please adhere to him. He's asking the class rep's contact. So please, whoever is a class rep, kindly share your contact with him so that you can share the meeting tutorial links with you guys, right? I think I only have one guy. Is it Charles? Yeah, I think Charles. Charles, are you on the call? Yeah, there's some Charles I have. So, Calvin, I'll send that Charles contact to you. If not endurance, I'll send it to you in the chat room. You just give it to him. He's the one I normally deal with. So 455 7. I think the last one he was one who communicated with you with the meeting, right? So I'm assuming he's arrived. Okay. So endurance, share it with Kevin on the page. Yeah, I think that's it. So we can move on. All right, so you can give this a try. So you want another example? This is another example for you. So try this. Find F2, F3, F4, and F5 if F is defined recursively by F of 0 equals to -1, F of 1 equals to 2, and for N equals to 1, 2, all the way to positive infinity. For N equals to 1, 2 to positive infinity. Then you can have F of N plus 1 to be equal to F of N minus 1, all divided by F of what? N. Can we also try this?
So I'm done with the first one.
Okay, please. So what did you get for the first one?
Minus half.
Minus half. Okay. Let's all try it together and let's see what happens. So for F2, what do you think you have to do? Anyone? If you want to find F2, because you are given F of 0, you are given F of 1. If you want to find F of 2, what do you do?
So you take N is equals to 1, then substitute it inside this thing, the function.
You take N equals to 1.
Yes.
Okay, and you make a substitution. So let's see. If you take N equals to 1, watch this. Here, right? N is 1. So I'm going to have 1 here. N is 1. I'm going to have 1 here. I'm going to have 1 here. So that's now going to give me what? My f of 2, straight up. Because it's going to be what? 1 plus 1. So that's going to now give me f of 2. Now to be equal to f of, this is going to be what? 1 minus 1, which will be f of 0. Divided by, this is f of 1. So when I'm here, the next thing I'm doing is simple substitution. Because my f of 0 is -1, right? That's it. Maybe I'll use another marker again to see. F of 0 is -1. So I'm going to go to equal here. F of 0 is -1. F of 1 is +2. So that's not going to give me what? Negative half as to mention. Now, if you also want to get the f of 3, then of course your n should be equal to 2. So that would be 2 plus 1. That'll give me f of 3. And then here should be f of 2 minus 1, which is f of 1, all divided by f of 2. But I already know f of 2 to be -half, which is the denominator. And I already have f of 1, which basically was given a question as 2. So I can do that substitution, and that should give me my answer for f of what? 3. So with that said, when I make the substitution n equals to 2, I'll be able to land up with my f of 3. Again, if I also made a substitution of n equals to 3, I will land up with what? My substitution of f of 4. And lastly, when n equals to 4, I can be able to land up with my value of f of what? 5. And that's it. Any questions so far? Any question? Good. If there's no question, then we move on, right?
Like I said,
Yeah.
okay, so please can you go to the yes. So it's a matter of making sure that the first for this like instance f of n plus 1, you have to make sure that, let's say, when you are being given let's say n equals 4, you have to make sure that let's say you have to use the previous one that you did. Let's say, for instance, f of 3, the answer that you got, you have to replace it here. Or
Yes. That's what we are saying. Recursive is a matter of calling an object itself a number of times. So you are calling
okay,
the previous one the next to get the current one. And when you are the
okay,
current one, get the next one, you need to be able to use the current one to get the next one. If you're the next
okay.
one, to be able to get the next one, you need to use what you are the next to get the next one.
Oh,
So
I
we
see.
can't keep always calling the previous one to get where we are going until
Okay.
reach the completeness. Okay,
Thank you, sir. Thank you.
great. So let's look at this example again. So write a recursive definition of the summation of AK, where K will start from 0 to N. And with this said, it is easy to be able to know that if I'm supposed to be able to write this initially, I'm going to have something like, when K is 0, I'm going to have A0. Okay, this symbol means sum. So I'm going to bring the plus here, and then I can now go to look at A of 1. So that will be A of 1. And then the next one I'm going to look at will be, when K is 2, I'm going to have A of 2 plus positive infinity to, when K is N, I'm going to have A of N. Okay, so basically that's how the sum is going to be. If you don't know this, I'm telling you, this is also for the product, right? So imagine you see this. This is only the pi 22/7, but it's also for product. So I'm having K starting from 0 again here to N. of AK. So this means that I'm finding the product of the AKs. It's going to be A0.
First one, flag hand. It's
All
only
the
some other flag hand on my account.
Yes, mute.
First one.
Okay, so that's it about this as the product. Now let's come back here to the basis step. We know that the basis step here will be the A0. So by this situation, what we have is that the initial value, which is the basis step at 0, is going to be AK, and the summation of AK, K starting from 0 to N, to be the same as the A0. Now with that said, we can now be able to increment it. If you check here, if I'm at 0, I incremented it by 1 to get A1. If I'm at 1, I incremented it by 1 to get A2. So when I come here, all I'm going to do is I'm going to pick the initial step, which is what you are seeing here. And I'm going to add on another subsequent value. So it would have been just A1. If I just do A1 here without this, then that's going to be this plus that. So if you check, I'm replacing the whole of this here. This is it. What I've underlined is what is here. And that's what we are seeing here. That's the A0. Plus the subsequent one. If N is 0, as we always try and do, this is now going to be what? A of 0 plus 1, which is A1. And that A1, it means that I'm just going to add A1 to the initial step. When I add A1 to the initial step, I'm going to get a new sum. And that new sum I'm going to get, I can now be able to add another 1 to the N. So instead of N being 0, now N will be 1. If N is 1, I'm going to have what? A of 1 plus 1, which will be A2. And that should be able to help me to get it. So now I have to add A2 to the previous sum. Then I cannot increment it from N, which was initially 1, to now N to be 2. So that will be what? A of 2 plus 1, which will be A3. So I'm now going to have some A3 added on to that. And that's what you can have on the table. Okay, now the second worked example has to do with what? Fibonacci sequence. For Fibonacci sequence, guys, hold on a second. All right, let's continue. So when we talk of a Fibonacci sequence, right? Or Fibonacci numbers, basically what we are referring to as to do with what we refer as a set of numbers that start from 0, right? The next one should be a 1, and then the next number in the sequence should be the sum of the first two numbers, okay? Or it can also be, in this case, a Fibonacci sequence will start with 1, the next number would always be a 1, the next number will be the sum of the previous two. So that's it about a Fibonacci sequence. So it's any set of numbers that either start with a 0 or start with a 1. And then the next number should be mandatorily a 1. And then the next number should deal with the sum of the first two numbers. Okay, so what does it mean? It means that if I'm starting with a 0, from the rule, the next number should be 1. From the rule, the next number should be the sum of the previous two. 0 plus 1, that'll give me a 1. From the rule, the next number should be the sum of the previous two. 1 plus 1, that'll be 2. From the rule, the next number will also be the sum of the first two. 1 plus 2, the previous two. 1 plus 2, that'll be 3. The next number should be the sum of the previous two, which is 2 plus 3, that'll be 5. The next number should be the sum of the previous two. That'll be 3 plus 5. That should be 8. Then I can be able to have these numbers to positive infinity. Can you see that? Again, I can also have it starting with a 1, right? Remember we said I can either start with a 0 or you can start with a 1. So if I'm starting with a 1, mandatorily the next number should be 1. The next number should be the sum of the previous two, which is 1 plus 1, that gives me a 2. The next number should be the sum of the previous two, which is 1 plus 2. That should give me a 3. The next number should be the sum of the previous two, 2 plus 3, which is 5. Right? And then you can also do 3 plus 5, that would be 8. If you want to go ahead again, you can do 5 plus 8, which should now give me a 13. And that should be able to do this all to positive infinity. Right? So that's it about for the Fibonacci sequence. Okay, with this said, we can now be able to see how best we can look at what is on the table, right? With regard to the initial step, and then the initial step basically is dealing with f of 0 to be 0. Well, let me finish the class. F of 1 to be 1. And then the next one will now have the generalized recursive function or recursive definition, which now becomes f of n to be equal to f of n minus 1 plus f of n minus 2. And how do we do this? This is very simple. It means that if I'm going to start from here, the logic thing is that I have f of 0, f of 1, right? Which the next thing I need to do is to get f of 2. So I have to make a substitution of n equals to 2. So this will be 2. And then this one will be 2 minus 1. Can you see that? And this guy should be 2 minus 2. So if you check well, I can now have my f of 2 to be equal to this guy, which is 2 minus 1, give me 1. So that'll be f of 1 plus this guy, which is 2 minus 2, give me 0. So that'll be f of 0. Now watch this. If you want to get f of 2, is a f of 0 plus f of 1. F of 0 is what? 0. F of 1, we're given initially to be 1. And that should be able to give us what? A 1. And that's the one you are seeing here. So if you do that again to be able to get f of 3 with n equals to 3, you should be able to have f of 3 minus 1, which is the same as what? F of 2 minus, sorry, plus, I'm sorry. N is 3, all right. Okay. So that's going to be f of what? 1. And that should help us to be able to get our f of 3 we are looking for. Now with that said, we can now know that f of 2, which you saw from the previous iteration as what? 1. I already know f of 1 from the question here as a basic step to also be 1. So that will now give us a f of 3 to be 2. That's what you're also seeing. So you can do that iteratively until you reach what we call convergence or ergodicity. That's it. All right. Now, if that is okay, we can now move on. So now let's move on to look at sets. So for sets, we already saw sets, I think back in session 5, if I'm not mistaken, yeah. So set of all positive multiples of 3 can be recursively defined as, we can have multiples of 3 is basically 3, 6, right? 9, and then 12 all the way to positive infinity. So the first basic step will be 3 belonging to S. Then the recursive step will now be if X is an element of the cap set S and Y is also an element, then we can be able to concatenate and add them. So what does it mean? Assuming this 3 is X, this guy is now going to be 3 plus 3. That will give us a 6. Then when I'm at a 6, I can still add on so that Y here will always be an increment by the 3. And the X will keep on changing. So if I'm at 6, I can now add on this to it, and that should give me 6 plus 3. That'll give me a 9. And then the 9 now become like an X. Then I can keep on incrementing it until I reach convergence and I'm done. The same applies to example 2, right? Which is dealing with even numbers. Even number is any number that when it's divided by 2 will not leave any remainder. So you should know by now that what you know back in your senior house as even numbers as 2, 4, 6, 8, 10. In the university level, we should also prove to you that 0 is also an even number. Why? Because if I have 0 divided by 2, I'm going to get 0 without any remainder. So even numbers actually will start from 0, not 2. So we're going to have 0 as a basic step for the even numbers. And then I can now go ahead to be incrementing it by what? 2 always. The same way I could have done the same thing here by having x plus 3 always to it. That's the same thing. Now the next example also, so that one too is not wrong. If you do that, it's right. The next example will also have the set sigma star of all strings over the alphabet sigma is defined recursively as this. So this sigma will be the set of all the alphabets we have by A, B, C, D all the way to Z. And then we have the basic step. We can have some epsilon being an element of the sigma star, where this epsilon basically is the empty string. Now, if epsilon is a basic an empty string, it means that initially there is no character or alphabet in the string, which we are calling the sigma star. So in the recursive step, we need to be adding on some alphabet to that particular empty string. And how do we do that? If let's say W is basically an element of the sigma star, right? Which is the string initially implemented, which we are saying that it's already empty. And X is an element of the set of alphabet A, B, C, D, all the way to Z. Then I can be able to concatenate what is currently in the string sigma star with an alphabet X from the set of alphabet A, B, C, D to Z. When I do that concatenation, X concatenated over to what is in the string. Previously, the string was empty. If I add
We do. Is it me or the lecture is gone?
He's gone. He's gone.
We're free. We're free.
Yeah, okay. I don't know, say network.
Or that no.
Please keep quiet
I
and
hope so you guys
concatenate
will see talk.
Because na
Concatenate.
yes ade.
We dey come concatenate.
Yeah, network, no.
Ẹyẹ
Yeah.
network cancer na yes ade.
concatenate yourself.
Every network, every
I hope
network.
you guys
We
will
dey
see
Ẹyẹ
come
network.
concatenate now.
Ẹyẹ network. Ẹyẹ cancer
Eh,
na take you over
I
the
hope
share.
I hope you guys
That's
will
why.
see talk.
On mama pura. Any. Sorry. Yes. Hey, someone mentioned my
yeah,
name.
It's being recorded. I hope you
Uncle
guys.
President, now where?
I got
Now
it
who
from
for
there.
President?
End the recording.
Hey,
Yeah.
and I'm not
Please
what
end
she
the
is.
recording.
Must have made it diagram.
Please end the
As well.
Just continue, guys.
Nah,
Please
lecture,
stop
no,
your
Johnny.
banter and ranting, my beg.
Please
Yeah,
try
that's
to
my
end,
phone.
end the recording. The recording.
Yeah, mo ko ba bim dawai.
I'm not sure why my table net is messing up. Just a second, guys.
Yes, please. You can.
Yes, that's it.
Yes, sir.
All right, that's fine. So I think we can continue. I don't know what happened with my MacBook, but we are good. All right, so I think this is where we got to. Yeah, so I was able to explain that once it is empty, you can add on to it, and that should be able to help you to get the concatenated version. And that is all about you call it the previous W, which is the string, or what is currently contained in the string a number of times together. All right. So now let's do correlation. What's the time? 15 minutes. Let me see whether I can. Relations is not going to be difficult, but please pay attention here, okay? For relations, we are looking at the relationship or the association between two sets, in my opinion. Let me put it in that way. So I can be able to have the two sets. Okay. So we say that the relationship or association between elements of a set are represented using the structure called a relation, which is a subset of the Cartesian product of the set. Quite. Relations can be used to solve problems. Relations can be used to solve problems such as determine which pairs of cities are linked by air flights, finding a viable order for the different phases of a complicated project. Sometimes also we can use it to produce useful way on how we can store information in a computer database, or how we can retrieve this data from tables in a computer database as well, right? Let's go ahead and look at some terminology. So set of ordered pairs represent the relationship between elements of two sets, and hence we call it the binary relations. So normally a binary relation from a set A to a set B is represented by the Cartesian product of A and B, which normally is denoted by the R, right? And that is where our focus should be, binary relation, looking at two sets on the table. So the notation A, R, B is basically the same as saying that A and B are related. If you have this, it means that A and B are not related. Or sometimes you can also use this to denote that A and B are not related. There's no association or correlation between A and B. When A and B are related, A is said to be related to B, that's it. If the relationship among elements of more than two sets, for two sets, we say it's binary relation. What if it's more than two sets? We call it the n-ary relations, where n will determine the number of sets. So if it's 3, you can replace it in that way. That's it. So we still come back to the binary relations. Let A be the set of students, B be the set of courses, right? So you are my student, level 100 students reading distance, BSc IT. And then there are courses you are doing like introduction to computer science, like mathematics for IT professionals, the other courses you're doing. So the relation R that consists of the pairs A, B may represent that A is a student enrolled in a particular course. So if I pick a random name on the course, right now I can see a name like Abdul Malik, right? Abdul Malik is enrolled in a course DCIT105, which is maths for IT professionals. Again, you can also do it. City A is in that particular state B. So that's for the other pairs, we can have Boulder and Colorado, all the way to hitting Red Bank and New Jersey as cities within their respective states in the USA, right? So another thing too is that we can also represent relations graphically, okay, or in a tabular form. So let's assume that we have two sets. The first set has 0, 1, 2 denoted with a set A. The second set has AB denoted with a set B. So we can define this random relation, right? 0 from set A is related to A in set B. Then we can also have 0 in set A related to B in set B. 1 in set A related to A in set B. 2 in set A related to B in set B, right? Now with that, we can now say that this is basically a relation from A to B. So we can't say that, we can say that 0 is related to A, which is true. From here, 0 and A are related. Can you see that? But what can't we say? We cannot say that 1 is related to B. 1 is rather related to A, but 1 is not related to B. Don't ask why. It's a particular example, okay? So it is not always mandatory for every element in the twos across the two sets to be related. So if we want to represent it graphically, then we can list the set A elements here, 0, 1, 2. Then we can also list the set B element A and B. Then we can now strike the relation from A to B, 0 all the way to A, from what we have here, which is this. Then we can now go ahead to also have 0 is related to B, 0 is related to B. Then we can have 1 is related to A, 1 is related to A. Then lastly, we can have 2 is related to B, 2 is related to B. Now, in terms of tabular form, we can also have this, okay? We can have our 0, 1, 2 from the set A, AB from the set B. Then if there's a common intersection or overlap between, say, 0 and A, which is true, we can now represent it that. Is there anything like 0 and B? Yes, we can put it here. Yeah. Is there anything like 1 and A? Yes, we can replace it here. Is there anything like 1 and B? No, that's why there's nothing there, because if you check the relation, there's nothing like 1 and B. Is there anything like 2 and A? No, from the relations given, we don't have. But is there anything like 2 and B? Yes, we have that. So that's it here. Okay, so that's how we can represent relations graph. Now, let's start with the properties of relations. So there are about 3 main properties we're looking at: the reflexive property, or the property of reflexivity. And then the other one has to do with what we call the symmetric property. And then the last one has to do with what we call the transitive property. Now, with these properties, let's start. As we move on, I'll explain it as we move on, right? So we're starting with the reflexive property, right? Or the property of reflexivity. A relation R on a set A is called reflexive. If A is related to A, in other words, if an element A in the set A is related to itself. So the element A doesn't have any other frame by itself. So in that case, all the elements in A should be related to itself. So let's assume that the set A contains 3 elements, 1, 2, and 3. I should be able to see 1 is related to 1. I should see a 2 is related to a 2. And then I should see a 3 is related to a 3. That is what it means that a relation R on a set A is called reflexive if A is related to itself for every element A in the set A. So if the set A contains 1, 2, and 3, then we can easily be able to have all the 3 elements related to itself. Okay. Now a relation R on a set A is irreflexive if for every A belonging to A, we cannot see, let's say 1 is related to 1, you cannot see 2 is related to 2, you cannot see 3 is related to 3, as the example I cited earlier on. So in that case, we call it irreflexive. Let's look at an example. So this is an example whereby you're going to have the set containing 1, 2, and 3. 1, 2, and 3, and 4, right? So for us to be able to judge that each of these relations, 6 relations on the table, is reflexive, then I should be able to see this. 1 is related to 1 here. That's a secret. So 1 should be related to 1. Which is good. So this can be what? Reflexive. Now when I come to R4, do I see 1 is related to 1? No. 2 is related to 2. No. 3 is related to 3. No. 4 is related to 4. So this guy is not reflexive. Rather, we can call it what? Irreflexive here. So for irreflexive, a relation R on the set A is irreflexive if for every small a belonging to cap A, that particular element, like 1, 2, 3, 4, is never related to itself. So this is a typical example of an irreflexive. Now let's look at R5. 1 is related to 1. 2 is related to 2. 3 is related to 3. And of course, 4 is related to 4. So with that said, we can draw a conclusion that this is also what? Reflexive. This is not, is irreflexive. So this one cannot. So in that case, we can only conclude that R3 are next. Okay, we move on. So that's it about reflexive property. Let's look at another example. So we consider these relations on the set of what? Integers. Okay, so we're going to have R1 to be this all the way to R6. So let's start. When we start with the first one, A is less than or equal to B. There is equality inside. So no matter what it entails, we can always have something like what we had here. Let's say the R5, 1 is related to 1. Guys, go to this room. Go to this room. 2 is related to 2. 3 is related to 3, and 4 is related to 4. So basically, we're going to have something like this. But the only key difference is that there are going to be instances whereby the second element would always be bigger than the first element, or they'll be the same. So that's the meaning of this. This is equal to or less than. So with that said, we can say that this is also reflexive, R1. Now when I come here, this means that if my A is 2, my B should be 1. So they can never be equal. So this guy can never be what? Reflexive. This means that I can have this or I can have that. So if A is the same as B, that means I can have 1, 1. I can have 2, 2. I can have 3, 3. I can have 4, 4. But in here, I can only have something like what? 1, -1, 2, -2, 3, -3, and 4, -4. So with that said, we can also say that R3 is reflexive. Now we go to R4. R4, you don't need a switch here because this is really equal to. But that's also reflective. Then we can now go ahead to look at R5, which is A equals to B plus 1. And this one, no matter what, the left hand side and the right hand side will not be the same. That's correct. So this cannot be reflexive. Lastly, this will also not be reflexive because let's say if A is 0, B is 0, you get a value less than that. If A is 1, B is 1, you get a value less than that. But if A is 2 and B is 2, you're going to get 4. So that one too cannot be reflexive. So it's only R1, R3, and R4, which are reflexive. So far, so good. Because of time, should I end here?
No, don't answer.
I should continue. All right, good. Let me finish. Let me continue. For let's look at a symmetric property. So for symmetric property, it's very simple. If I have Kofi is related to Amma, Amma should be related to Kofi. Please, you understand? For symmetric, if I'm related to you, you should also be related back to me. So that's why you say that a relation R on a set A is called symmetric. If B is related to A, whenever A is related to B, for AB belonging to what? Cap A, which is a set. That means that an element is related to a second element if and only if the second element is also related to the first element. And if an element is related to a second element, but the second element is not related to the first element, then that particular relation is said to be what? Not symmetric. So that's it about the symmetric and non-symmetric. Now with that said, let's quickly look at an example. So the relation consisting of this space, I'll skip this one, right? So let's look at a better one. Yeah, let's see. We come back to the same example we're trying to look at. So the set contains 1, 2, 3, 4. And then we want to be able to look at these relations and then judge which of them is symmetric and which of them is not. Okay, quickly. We have this. Oh, guys. So R1, if I am supposed to see 1 is related to 2, I should see a 2 is related to 1 back. Check back the definition, right? Definition says that a relation R on a set A is called symmetric if for any B related to A, there should also be what? An A related to B. This means that if an element is related to a second element, an element is related to a second element if and only if the second element is also related to the first element. So we come back here. We have a 1 is related to 2. Okay, with this 1 related to 2, I should also see a 2 related back to a 1. Now, if I go to a 3 is related to 4, I should see a 4 is related to a 3. I don't see that. If I pick a 4 is related to 1, I should see a 1 is related to a 4. I don't see that. So because of that, this cannot be reflexive. Oh, sorry, symmetric, sorry. Now when I come here, 1 is related to, oh, please stop writing on my screen. When I come to the second one out to, please, I'll finish one and so relax with me. If 1 is related to 2, then I should see a 2 is related to 1. That makes it what? Symmetric. Now, the third one is 1 is related to 2. I want to see a 2 is related to 1. Is here. 1 is related to 4. I want to see a 4 is related to 1. Is here. Yeah, that's it. So with that said, I don't want to worry much about the reflexive. Hold on, I'll talk to you about that one shortly. So we can say that R3 is also reflexive. Now let's come to R4. 3 is related to 1. Is there any 1 is related to 3? No. And lastly, 1 is related to 2. Good. Is there anything like a 2 is related to 1? Watch it war. No, there's nothing like that. So this one 2 is out. And lastly, when 3 is related to 4, I'm not seeing a 4 is related to 3. So with that said, we can now conclude that R2 and R3 are the symmetric, are the ones exhibiting a symmetric property. Is that okay? So for symmetric, anytime I see any possible pair, I should see the vice versa pair there. We look at the antisymmetric. Antisymmetric is very simple. What antisymmetric is saying is that is the opposite of symmetric. If 1 is related to 2, I should never see 2 is related to 1 in the relation. That's why I say that a relation R on the set A such that all A and B belonging to cap A, if A and B are related, then B and A should not be related. That's antisymmetric. This means that, or that means that a relation is antisymmetric if and only if there are no pairs of distinct elements, A related to B, such that A is related to B, but B is not related to what? A. A relation cannot be both symmetric and antisymmetric if and only if it contains some pairs of the form A is not equal to what? B. So for A equals to B, we are exhibiting that reflexive property. And for reflexive property, we are saying that anytime T I have 1 is related to 1, I can duplicate it. And that should be able to also give me another one is related to 1. If you guys remember the example we saw back, I think there was an example with 3. Let's see, another 3. This is the same as the second component 3. All right. So if that's the case, then I can be able to replicate my 1, 1 to make it 1, 1, another 1, 1. So that one of the 1, 1 will take AB, the second one will take BC. BA, sorry. So for antisymmetric, if I see this 1, 2, I should not see a 2, 1. So this is wrong. Now, if I see a 1, 2, I should not see a 2, 1. This is also wrong. Because if I'm doing antisymmetric, I should only see this. A typical example is this guy. See this one. 3 is 4, right? There's no 4 is related to 3. Now let's go to R3. 1 is related to 2. 2 is related to 1. That's also wrong. So R4, 2 is related to 1. Is anything like 1 is related to 2? No. 3 is related to 1. No, 1 is related to 3. 3 is related to 2. No, 2 is related to 3. 4 is related to 1. No, 1 is related to 4. 4 is related to 2. No, 2 is related to 4. 4 is related to 3. No, 3 is related to 4. So that's. And then lastly, if my 1 is related to 2, There's no 2 is related to 1. Can you see that? Yes. If 1 is related to 3, there's no 3 is related to 1. If 1 is related to 4, there's no 4 related to 1. Such that R is both symmetric and antisymmetric. And then R is neither symmetric nor antisymmetric. So can you get some examples when I meet you next week? We can take it out from here. So far, so good. Any questions so far? Please take a snapshot of this. Okay, so if there's no question, then I think yeah, okay.
Sir, please, when is DC105 lectures ending? Like officially for just like the other ones?
Sorry, I don't know. Charles, when are you guys in your lectures? When are you writing exams? Is the provisional timetable out?
We have one on Sakai saying that examinations will start on the 26th
of this month.
Yes, that's what we have.
It means I have like 2 weeks more to go. Right? Is that not it?
Yes, sir.
Okay, so next week when I meet you, I'll finish the transcript. Then I'll go ahead and start with the next 10. That will be on Tuesday. Right. Any question on my table again?
Sir, please, I have a question. Please, can I? Yes.
Right. Someone is asking a question. Is there any question?
Sorry, sir. Sir, I was asking, can you hear me?
Yeah.
Yeah, please, I wanted to know just how can I just want to go over this if it's possible. How can you make sure it is anti-symmetric as well as symmetric? That part I just didn't get that part.
You mean the assignment I give you?
Yes.
It's an
When
assignment.
you were explaining, yes, please. When you were explaining, you mentioned how to ensure that the relationship can be symmetric as well as anti-symmetric. But in the explanation that followed, it looked to me like
That means I've solved the question with you guys.
all right. I just wanted like an
Yeah, I'll get
explanation about
your issue has to do it. I'll give you a clue. Your clue should look at reflexive property. That's it.
Okay.
So you can meet in groups and discuss. Right? You don't need to submit it to me though. You just have to look at the next week. Okay.
All right.
I
Thank you.
will.
Sir, please, the slides.
I'm going to upload it there.
All right. Thank you, sir. God bless you.
Right. Please, is there anything?
Hello, sir.
Yes.
Sir, please, the assignment, is it a try work or information?
What's a try work? Just a try work. Right.
Okay.
I'll try and get you guys some assignments. Maybe if not anything at all, like a take home quiz for you to do for assessment, right? So I'll do that. Okay. Next, you're gonna meet
Sir,
you.
please, are you not having any tests?
So that's why I'm saying that I'll look at it next week when I meet you. I'll see, right? So that I can use that as in addition to the assignment you have given, right?
Okay.
All right, guys. Okay, if there's nothing on the table, let me know you guys, and then I'll upload this now for you to look at it. Right. All right. All the best. I'll see you guys next week. Right.
Okay, thank you, sir.
Thank you, sir.